Update the particles. Okay, should be streaming now. Just check it. Okay, Twitch is working and YouTube is working. Nice. Well, hello guys, today we'll be working on adding some user input to the game. Yeah, let's get into it today.
Devices support the mailbox present mode may have already run into the problem where their animations run very quickly. My computer does not support this present mode, but if I uncomment these lines to run using the immediate mode, you can see what I mean. We need to implement some sort of timing mechanism in our loop. One way that we already know how to do this is by synchronizing with the display's vertical sync by using the FIFO present mode. But one big issue with this approach would be that the game would run faster on displays with higher refresh rates. For example, the cube would spin twice as fast when played on a 120Hz monitor compared to a 60Hz monitor. Game loop timing is a surprisingly complex topic, and it is a pretty unique problem to the domain of making games. Not many other applications require user interaction in real time while also simulating multiple different subsystems such as AI, physics, audio rendering, and more. In this tutorial, I will present a very simple solution that will work well for now, but is really just the tip of the iceberg. There are many ways to make a bad game loop, so I recommend taking a look at the article's game loop timing and fix your time step. Links are in the description below. Also, Game Engine Architecture by Jason Gregory has an entire chapter dedicated to just this topic. The basic idea behind a game engine is that it consists of various systems, with each system being capable of advancing by a certain
I guess it never occurred to me how complicated it could get. But,
amount
well,
of
let's
time.
get
The
into
amount
it.
of time we advance the system by is called the time step. It is also commonly referred to as delta time, or dt for short, as it is the difference between the current time and the time the system last ran. If we make it so that each system can take a variable size time step, then we can render the game at as high a frame rate as our computer can achieve without issue. For high frame rates, we essentially are just taking more frequent and small time steps rather than a few large ones. Okay, let's get to coding. First thing we're going to do is include the chrono header in the app implementation file. Chrono is
Okay, in the app implementation file, let's close all these other ones. Okay, and first up CP, first HPP. I'll both of them here. Hash include array.
we can use to get a very precise reading of the current system time.
Hash include chrono. I remember yesterday that
Time with high precision.
they said there was some
Now to add some timing
comment about it. They are using C++ 20 STD chrono duration works different with STD ratio as a second parameter. So yeah, looks like this episode has a lot
capabilities to the
of
game loop. Inside the
updates to
run
be
function,
added
just
to
above the
it.
while loop, declare auto current time is equal to STD chrono high resolution clock now.
Auto current time STD high resolution clock.
We get the amount of time that has elapsed per iteration of the loop. So declare auto new time is equal to STD chrono high resolution.
Yeah, let's give that caveat adding it. auto new time.
now, and we can just copy and paste this from just above. We declare this after the glf
Yeah.
because the function call may block. For example, while resizing, the whole program pauses, and we need the amount of time elapsed to be accurate. Next, I will calculate the amount of seconds elapsed with float frame time is equal to std chrono duration.
Chrono duration.
With float
First
comma
we'll
std
save
chrono
this
seconds period
version.
in angle brackets, and then new time minus current time as the argument, and then all of this followed by dot count. So if half a second has passed since the last loop iteration, then frame time will be a float value of 0.5 for half a second. Then set the current time equal to the new time, since we need to store the current time value for the next iteration of the while loop. Next, we could make the simple render systems
Yeah.
render function take a time step value, but for now it isn't really necessary. Instead, let's just delete these two lines from the simple render systems render.
Simple render system. Did we save? What are the changes here? Okay, match. Erase. Just delete this. And delete this. Yeah, that's like a minor issue. Let's not done with this 14 camera field. Button push. Yeah. Now the new Chroma stuff is there. I'll leave it for now, but maybe later we can just delete it.
Since updating an object's position in a
Okay, simple render CPP. For loop. Yeah, not deleting this. Oh, here just combine these two together.
systems render function. Since updating an object's doesn't make much sense. Okay, the code should build and run, but now all we've got is a cube that doesn't move. So I'm going
Okay, let's test it. Yeah, just setting up. Cool. After user input.
a new file called keyboardmovementcontroller.hpp. This class will be a simple example of how to get user input from the keyboard and use it to move game objects in real time.
Yeah. New folder. That's all. Keyboard movement control. Clear it out.
We start off by adding a header guard.
A hash include a weekend object, hash include a window. Notice include namespace we plus keyboard movement control.
Within the keyboard movement system class. This struct will store the relationship between different movement actions and the GLFW key codes. So for example, for the first member, I'll have int move left is equal to GLFW key A. This will bind the
Create
to the move left action. I've included the struct definition in a paste bin link below to save you all some time.
Okay, that's good. But map this way. Yeah. Control C. Also need public. DWS. Do left, right, up, down. Yeah. Let's continue.
This class will support 10 different actions for moving a game object. Translation up, down, left, right, forward, and back, as well as rotations to turn the object to its left or right and to left, up, or down. The key mappings have default values set, but these values can also be changed at runtime. Add a member variable with type key mappings called keys to store the movement controller's mapping initialized with the default values. I will also
Key mapping. Yes. Only that float move set must be float looks speed 3.0 and 1.5.
controller will move and turn the game objects. I find 3 and 1.5 make good default values based on what we've got so far. Okay, now to add an update method, we have void move in plane xz. I call it this just to signal how exactly this movement function will work. This function will move a game object with the controls being relative to the direction the object is facing within the xz plane. Of course, there are many other possible ways to map user input to movement. This is just one method I personally find intuitive for controlling a first-person camera view. So the
Void move in plane C. Rotate camera. Left window, delta seconds, game object.
Is a GLFW window pointer, followed by a float DT value for the time step, and finally an LVE game object reference as the target object by the controller.
Changes to DP. DT.
Here means that there is a dependency on the keyboard movement controller to the GLFW library. For this tutorial series, it doesn't really matter since I will only ever be using GLFW, but if you plan on supporting other windowing systems, then you may want to create a more complete abstraction for user input devices that is not dependent on any specific windowing system. Okay, now let's create the implementation. First, copy the move function signature, and then I'll add a new file called keyboardmovementcontroller.cpp. First, include the keyboard.
This wasn't required, but let's leave it. New C++ source file. Shift F6. Rename. Copy. Cancel. Function scale. Okay, let's make a new one here. Source file, copy paste.
Controller header file. Then add your namespace and paste in the move function signature. Then add your class's name scope before the function's name. Okay, so we'll start.
Okay, I should include keyboard movement http namespace OBE and finish its analyzing. Avoid keyboard movement to movement. See. Let's see what the code is.
GLM-3 variable called rotate, initialized to 0. We will use this to store the user input for the rotation values. Next, we need to check which keys are currently pressed down. So in an if statement called glfw get key, with the first argument being the window pointer, and the second argument being whatever key code is stored in the keys.lookWrite field. We can check if this value is equal to
Windows key is lookWrite.
glfw underscore press, indicating that at the time the glfw pull events function was last called, the lookWrite key was currently pressed down. If this is true, we are going to take the rotate.y value and increment it by 1. Then duplicate this if statement and update to check the key code for looks left, in which case rather than add 1 we subtract. Next, duplicate both these lines and do the same for the lookup and look down keys.
Where should make this? Look and look and Linux here. Word.
Where instead we add or subtract 1 to rotate.x. Now that we have this variable storing the current rotation inputs, we can add it to the game object's rotation transform value. So game object.transform.rotation plus equals look speed times dt times glm normalize rotate. We scale the rotation inputs by look speed and delta time so that
the game object transform plus equals transform dot translation. Right. Rotation look speed dt star dt star glm normalize rotate. Rotate
in a steady manner independent of whatever the current frame rate is. I normalize the rotate variable so that the game object doesn't rotate faster diagonally than when rotating solely in the vertical or horizontal directions. When no keys are pressed down, the rotate variable will stay as the 0 vector. And if you try to normalize the 0 vector, the whole equation blows up. So to fix this, we need to add a check to only update the game object's rotation when rotate is non-zero. The best way I know how to check this for a vector is use the dot product with itself and check the inequality against epsilon. The vector dot product with itself is equal to the sum of the squares of its components. So this will be a positive value equal
Which okay, we're squaring it. Forgot to first add hash include limits. Hash include limits. So we have GLM dot rotate less than std numeric limits
to the square of the vector's length, and we can check using epsilon because it is always a good idea to avoid comparing a float value directly with 0. Next, I'm going to limit the range of the game object's transform.rotation.x value to be clamped between plus or minus 1.5. This roughly corresponds to 85-ish degrees. While
game object transform rotation dot x equals lamp
necessary, I do this to prevent objects from being able to go upside down. Then for the game
okay 1.5 f 1.5
transform.rotation.y value 2 pi. 2 pi is 360 degrees, so a full turn, and this prevents repeated spinning in one direction, causing the value to overflow. Okay, next we need to handle the translation
game object transform rotation dot y equals GLM mod. Okay.
actions. Then move forward, backward, left, and
Limit the h values to plus minus T5-ish degrees. Why don't you just do like 90?
all move the game object parallel to the XZ plane. However, they depend on knowing which direction the game object is facing. So I will add a float yaw is equal to game object.transform.rotation.y. Then we can declare the forward direction with const glm_vec3 forward dir with the values sine of yaw, 0, and cos of yaw for the x, y, z components respectively. To calculate the right direction, we must find the perpendicular vector within the XZ plane. So we will have const glm_vec3 right dir with forward dir.z, 0, negative forward dir.x. And this will be the desired perpendicular vector. Finally, the up direction is simply const glm_vec3 up dir with 0, negative 1, and 0.
Now, what are we setting all these vectors up for? Say float here, game object rotation at y, front right, and these are all constants also. For shaft f6 forward direction shaft f6 right direction Shift F6, up direction. Yeah, this is sine. This one is cos. Then right direction. Okay, wait. What are the values? Forward dot C and minus forward direction dot X. Newton. Curly brackets 0.0 F, comma minus 1.0 F, 0.0 F. That's all use now used.
Declare a glm vec3 move dir vector initialized with 0 to store the user movement input. And then we'll use the same method as above to get the keyboard input.
vec3 move direction 0.0 F.
Update the key value to keys.moveForward and then set move dir to plus equals forward dir. Duplicate this line, changing to keys.moveBackward and move dir to minus equals forward dir. And then it's just the same idea from the move left, right, up, and down actions. Just duplicate the lines.
I stay on setup, but whatever. Let's see. F GLF. Okay, is that need to be in the same function? Doesn't seem like it. Move control X. Move direction. Move. And move forward, move backward, then move up, move down. Plus forward direction, forward direction, move left, the right direction, left direction, and we don't need this. There are some more FCO, GLF W get key, window keys, no, move up, simply call GLF W script this of direction up or direction up. And what had happened to that? Is it not called left? Oh, yes, right direction. Yeah.
The key code being fetched, and update the move gear with plus or minus the right gear vectors for left and right movement, and plus or minus the up gear vector for up and down movement. Then, for the same reasons mentioned before, copy and paste this if statement for the purposes of checking that the move gear vector
If make this out direction, move direction. Then we might have to clamp it a bit. Translation, move speed.
So if we have if glm.moveDir, moveDir is greater than epsilon, then the gameObject.transform.translation plus equals move speed times delta time times glm normalized moveDir. Okay, now this function relies on having the glfw window pointer, which we currently have no way of getting. So let's open up the LVE window.
Okay, let's change this to be below. Control X. Control. Okay, so first it handles the rotation, and then it does this.
And add a new getter function with return type glfw window pointer called get glfw window. Let's mark this function const and simply return the window member variable. Okay.
And I go lv window.hpp. Steady. The standard hashtag library. Yes. Study the Yeah, nothing much.
And now let's create an instance of the movement controller and apply it.
So we have to make the variable get the function. And then as we added it, void reset resized window. Was window resized. Yeah, reset window. Yeah. Ensure of window get shell of window. This could be a const actually. Yeah, even he makes it a const. Const.
Implementation and include the keyboard movement controller header file.
First implementation. Dash include keyboard.
Currently do not store the camera's position or orientation in any way between frames. So I'm going to create a new game object within the run function using auto viewer object equal to LVE game object, create game object. This game object has no model and will not be rendered, but is just used to store the camera's current state. Next, declare a key.
Yeah. We're doing it here. Auto viewer object. Create game object. And let's rename this.
Controller called camera
Not in
with
space.
an empty initialization.
Camera control.
While loop, below where the new frame time is calculated, we add camera controller dot move in plane xz with LVE window dot get glfw window as the first argument, followed by frame time, and then finally the viewer object. This will update the viewer object's transform component based on the keyboard input proportion.
Camera controller. Move in plane XC. Window. Capture left window. Frame time. Right. Control X. Frame time. Viewer object. Handle controller dot look Linux only window get shell w frame time viewer object. As it going all the way there. Everything saved.
The amount of time elapsed since the last frame.
Could all just be in like one area. For now, let's just copy paste this. And only call first out, first single. As I show this printer. That counts no.
Finally, we need to update our camera object using the new state of the viewer object. We can do this with camera.setViewYXZ, passing viewer object.
Camera.set view YXZ and view object.transform inspection.
Translation for the first position parameter, and then viewer object.transform.rotation as the rotation parameter. Let's clean things up a bit by removing these unused function calls, and then if you build and run, you should now be able to control the location of the camera within the scene by using the WASD keys to move and the arrow keys to look around. And this should work the same regardless of which present mode you choose to use. If I go back into my swap chain to return to using present mode FIFO and run the application again, you can see that the camera moves at the same speed, even though the frame rate is now significantly lower. One last thing is if you try to resize the window while you have a key pressed down, with the current implementation, the game loop pauses, and when it resumes, the camera will move in one large jump, based on how much time has elapsed. This can be undesirable for certain applications, in which case you could add a limit on the max allowable frame time.
And all shell and min and max frame. Oh, he's just set the value. Well, let's leave it for now.
Okay, so we just barely scratched the surface on both the topics of user input and game loop timing. Based on the type of game you're creating, you may require different methods for controlling your.
Yeah, let's test if everything's working. Now, cats working. I should probably set my keyboard mappings to my call matrix. So sorry, S, this will be R, this will be F, F and what should be not F. So now let's retry it. Let's check in the physical PAs. Or I just change this to Q and E though. GFTADW. Let's try it now. As well, diagonal. Q, E. Okay, rotation is fine. Only this diagonal thing is a bit weird. Cancel. Let's see. Okay, rotation is fine. Right direction. Let me double check the values on GitHub. This is 15. Keyboard, let's see. Okay, that rotation and all is fine. Move left, move right. Move right plus, move left minus. Let's see. Let's line everything forward, backward, right, left, up, down, right, up, up, down, look right, look left. Up, down, right. Hmm. Let's see. Let's try it out now. Okay, I'm clicking left, turning the opposite direction. plus minus. Let's see in the comment any useful information as well. LCD ratio. Control C, what is this? New term, current term. And second, and back. Okay, I'll have to leave in sometime soon, but let's just fix this issue. Okay, this thing didn't work. Let's leave it. Okay, amazingly well explained. Understand the right hand rule. Let's see. Yeah, right direction, dual and cross. Let's try this. Z 0, 1.0, Z 0. Let's see if this improves. Yes. Okay, left arrow, right arrow. Script up, down, left, right, forward, back, fly up, fly down. Okay. This is much better. Let's see any other things. And a branchless style here. Static cost. Thank you because I'm not that experienced. Can look at what it needs to do. My testing this was measurably faster, probably not enough. Next, choosing the correct data structure. Hmm. Key bindings, rotate right. rotate left. It's either way, potential and epsilon flow. Stop this. Definitely volume. Just wanted to show potential mistakes. Windows key. What is the difference? Get key virtual of yes. Oh, he's put it inside the brackets. Okay. Hmm. Let's see any other things. Hmm. Okay, let's play and see. Hmm. Yeah. What is the value of this? Oh, vector 3 cross product calculator. Yeah, let's just see. 0, 1, 0 is 0 and 3. Or compute input interpretation and to see what it looks the cross product looks like, not this. But cross product calculator looks. Okay, it is 0, 1, 0. Let's make this 3, comma 0, comma 3. Okay, that was supposed to be a 0 over there. Let me share this. Control D. Forward direction. Let's see. Minus. Let's see how this works. I think that one was messing it up. Yeah, it is 0. This was like, yeah, this is much more correct. Okay, cool. Fixed up all the issues. Let's save it this time. Yeah. Okay, 15, use import, commit and push. Push. Okay, okay. Push is done. Okay, that's it for today. I have to go help my mom out with some grocery shopping soon.